studied in every university that has
pseudorandomness?
Yeah, only in specific university that are more
right. So every place you have like a researcher that does something related to that, you'll have that. And essentially every leading university in the US. In Israel, yeah, the two people that like are really pseudo-analysts are here. So it's Amnon. There are other people who do pseudo-anonymous, but so he doesn't. Yeah, like he left us. Like he did that in the 90s, and now he does algebraic algorithmic game theory. He's not in Israel; he's in Stanford, but he does teach pseudo-anonymous and also differential privacy. That's what he does. Yeah. Rango.
Actually, I have a question.
Yeah. But everyone else, by the way, David Zuckerman, Salil Vadan, he has like a famous course.
The distance between derandomization and pseudorandomness.
Right, that's a good point. Good question. Right. That's true. That's a good point. Right, so there's derandomization, and that's like a complexity thing. And there's pseudorandomness, which is like even more combinatorial, like things we did. So I like anything that you can use heavy math to solve. That's me. That's like I don't know why.
In life.
Ah, wow. No, not in life. Interesting. Yeah, maybe. But yeah, and so Amnon likes like solve problem in complexity. So when he teaches this course, and he actually does that in different like ways all the time, you will see like the NC1s and AC0s and see those things. And you won't see probably too much of like, for example, the thing we did with tournaments and stuff like that, which are only mathematical terms. Right, so that's the difference. But of course, they play along, like one way. I mean, pseudo-randomness helps derandomization, and that's it, of course. Right, and also in courses in derandomization, if I would have called it derandomization, I would have to put like the Nissan-Wigderson PRG. It's a shame that I didn't, but you know, because of the war, I didn't.
The course changed it because like
right.
Without the war.
That's true. Yeah. Right. That's a good question. What did we miss? And we missed that because I saw the. Actually, we missed that because I saw scale number 09. It's a Leo or something, right? No one calls it 09. Okay, so actually the initial course was supposed to be more advanced. So everyone should have known expanders and PRGs, and so that's why I just, you know, for the sake of just for safety, I asked you before if you know that, and most of you said no. So I decided to make it more elementary, not less fun, just more elementary. Yeah, slightly less fun. Right? But the things we definitely missed, and it was difficult for me not to do, is the Nissan-Wigderson PRG. It's not INW, it's just NW, the same N and W, Nissan-Wigderson. So that's a way of translating hardness of functions to randomness. It's a serious breakthrough in complexity because it showed that constructing PRGs, you know, sufficiently to suffice to a full BPP would yield circuit lower bounds that are way beyond what we can do. So that's like hardness. These are called hardness randomness trade-off, and it's kind of unfair. I didn't do that. Every course has that. I mean, every course in pseudo-randomness I ever saw. Okay. You know, and many people do more of like random restrictions type of PRGs, namely you construct. It's kind of similar to what we didn't polarize, but it's not the same. So you have a function you want to fool coming from a class that you want to fool. So you want to fool a class. So it turns out, you know, and there are different flavors of that if you're going to use a bit of randomness to sample some of the entries, usually it's pairwise independence. So say you chose those, it doesn't look random, but no. And then you put here truly random bits just for the analysis. Then it turns out usually that the remaining function in the expectation, so the function which is obtained when you average over all that, it's a smoother function, it turns out to be easier to fool. And you need to prove that, and then you put the PRG that fools that weaker class of functions. So you are kind of putting like your random bits here. And then you say, well, but I put uniform randomness here for the analysis, I cannot do that. So then you kind of recourse. You need to argue that this function usually is not harder than what it was. It's always the case because you just fix all the bits almost always, and you recourse. So that's whole methodology of constructing PRGs is something that I wanted to do, but I didn't. I think that's it. What more? Like what's I mean, some of you know pseudorandomness, so what's left? Samplers, right? So you know what? Even more so, like relations, connections. So Salil's that's good. So Salil's monograph on pseudorandomness is actually oriented towards, you know, it has constructions, but it's more oriented towards relations between objects. So for example, you can. So we showed. You will see today that expanders gives, you know, weak but extractors. And I will show you that today. And you can show that extractors are equivalent to what's called samplers, which we didn't talk about at all. That's what you said. And expanders give samplers, but you know, to some extent. And then there are also least decodable codes, which are in some setting are equivalent to extractors. And it goes on. You know, certain types of extractors are, it's not only that, are equivalent to certain types of codes. So ideas are getting formed from coding theory in our community back and forth. So relations, we didn't do almost any relations. I feel like it's not a good way to end the course because just accuse me of things I didn't do.
Maybe what's the future?
Oh, good. So definitely I think that this is the thing that you need to do. Definitely, it's really hard. I told you I always believe tilde, but never mind. That's one thing. In extractors, I mean, it's kind of that's what, sorry? That's true.
That
So,
will be the next.
that will be the next one.
And you have double thing.
Right. In extractors, you have like one time someone, Barak asked me, can you have a 1.5 source extractor? So I mean, good, of course. It was like Barak. So what he meant, I don't know what he meant, but what we made of it is that, you know, say for example, you have two sources X and Y, but you don't get access to them. So for example, maybe, you know, you have two n bits, some of them are of X, some of them are of Y, you don't know which is which. These are called interleaved sources. They have, you know, applications actually. And even a worse example, if you think about it, is that you get their sum, like bitwise sum. So now you can even like, and it turns out that the techniques we have to construct two source extractors are strong enough, you know, you need to work a little bit to actually extract from that as well. They're independent. They're independent, but you don't get any one of them. But it turns out our techniques are kind of linear friendly, so you can imagine get one. Yeah, what's next? I don't know. Of course, there are many problems in expanders. That's Gal, sorry, I forgot about you. Many problems about expanders, like what I told you about MSS, they didn't actually get Ramanujan graphs, they got bipartite Ramanujan graphs. There is a problem of getting Ramanujan graphs and using their techniques to get other stuff that we're doing. Yeah.
It seemed like presentations expanded. Like there was like an attempt to build like.
That's definitely not the way I want to. Yeah. Okay, so one word about edge codes, they're really cool and strong. It's actually very interesting to say it because you have 2 minutes, it's enough. So, I mean, the point about edge codes is that it's funny how we really understand, you know, the zeros of a polynomial. I mean, we have like, you know, Schwarzschild or what have you, but we don't know how to walk over the zeros of equipment. So if you tell me, walk over this set only, so take in F cube, it was supposed to be F cube by F cube. So if you take F cube by F cube, and you have the zero set of a polynomial, say this is your world. You don't live in FQ over FQ, you live here. So these are only the evaluation points you have and so forth. It turns out that to now apply polynomials that live here to FQ is extremely difficult. It's like you need like 3 fields theory, fields and metal winners to just give you the answers to questions like what's the distance. You have like street names for these people, not IAS. So it's really difficult, really beautiful. Like it's really crazily difficult, beautiful. And last time I gave the course, we actually finished half of it at the end, and it was very fast. And then we finished the other half in a seminar like we're doing now. And I don't think it's going to change because it was really tight in terms of time. So you should come to that next year. It's really, it's mind-blowing, beautiful. Algebraic geometric codes. Okay, so it was really fun teaching you. Thanks a lot. יופי, מקווה שזה הקליט.